Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Our today lecture is about the Compton effect. In the previous lecture, I talked to you about the photoelectric effect. Photoelectric effect, and I told you that photoelectric effect is the it was important for many reasons. First, it was the first experimental verification of the particle nature of light, and the second importance was that the failure of the classical mechanics to explain the photoelectric effect, and the third one was that I told you that it is low energy interaction of yeah, or the interaction of energy with matter. And I told you that low energy interaction because we use a common light, and which were having energy of the order of the uh, electron volt, right? Of the order of what? Of the order of the electron volt. Few electron volt, I would like to. Few electron volt. This is what we have studied in the photoelectric effect. Now here we have one of the most important effect known as the Compton effect. He studied this effect in 1922, and according to the Compton effect, it is an there is unusual result observed when X-rays are scattered on some material. So here at this point, I would like to tell you that this Compton effect is the low energy. That is, it is the intermediate energy interaction. Intermediate energy interaction. Energy interaction. That is, we cannot observe Compton effect by using the ordinary light. So definitely the radiation used are in the X-rays range. So they have the energy of the order of the few mega electron volt, right? That is I don't exactly remember the range, but I think that it is from zero point 0.5 to 1 MeV of the order of the million electron MeV, million electron mega electron volt. It is of this order. X-rays energy are within this range. So X-rays photon of this energy are capable to cause the Compton effect, right? You may check the range of the energy maybe in your book, right? So I'm sorry for that if I made it wrong. Because it is statistical and hard to remember the values by heart. The second important point here is I told that the in intermediate energy interaction, most importantly here also, that it is another experimental verification, another experimental verification, experimental, another experimental verification of the particle nature of light, of the particle nature of light, that light behave as particles also. Now right here I just first want to explain to you that like the photoelectric effect here, the Compton effect, that is the classical physics again failed to explain the Compton effect. By classical mechanics or a classical theory, And the classical physics says that when an electromagnetic wave is scattered off the atom, the wavelength of the scattered radiation is expected to be the same as the wavelength of the incident radiation. Here it is not the case. We have an opposite situation here. Contrary to this, the prediction of the classical physics experiment shows that observation, not just the experiment, the experiments show that when X-rays are scattered off some materials such as graphite, the scattered X-rays have a different wavelength incident from the incident photon, from the incident photon. And the change in the wavelength of the photon is equal to delta lambda. This change in the wavelength of the photon is equal to h by m naught c into m naught c, let me, yes, m naught c into 1 minus cos theta. This is the this is very difficult to move without keyboard. Okay, so here this delta lambda, it is the change in wavelength, and this change in wavelength is equal to the wavelength of the incident photon. Here there is the wavelength of the scattered photon minus the wavelength of the incident photon. This delta lambda is equal to this, and it will be equal h. H is a Planck constant, m naught is the rest mass of the electron into 1 minus cos theta, and where theta is the scattering angle. Now that is, I will explain these equations to you here, but the derivation is beyond the scope of your textbook, though they tried half, they neither derived nor left underived this, so they have put us in a trouble, but I will try to do it for you in a simplest way, right? Even if, because the derivation is not in the book, they just use the pick the important equation and place it there without being going into much detail. But here, inshallah, I will try to do it for you. The wavelength, second important point here is that the wavelength is independent of the intensity of the radiation. It is depend on the angle of scattering. Look here, that is the lambda dash equals here is lambda I into lambda I plus, that is, it will be lambda I plus h by m naught c into 1 minus cos theta. As I told earlier, that this uh, is the wavelength of the scattered photon, wavelength of the scattered photon, and here this is the wavelength of the incident photon, wavelength of the incident photon, and this portion, it is all constant, and if my memory is helping me, this constant is called the Compton shift or the Compton wavelength. Compton shift or Compton wavelength. Here H stands for Planck constant, and you know its value, Planck constant. It is the value of the Planck constant. M naught is the rest mass of the electron. M naught, the rest mass of the electron, rest mass of the electron, and c is the speed of light, of course, you know. And here the outcome is what? That the wavelength of the scattered photon is greater than the wavelength of the incident photon here. So there is a difference between the wavelength of the two. And oh, I'm so sorry, this is greater, right? So this is what the on the basis of the classical mechanics this cannot be explained. So let us start how. Here you see, for example, we have the graphite as the target nucleus. Here we have the X-ray source. And as you see here, we have the photon, as you see. And this photon has the wavelength lambda. And this is, as I marked already, it is the I. So here I will write lambda I. Right, the lambda I, the wavelength of the incident photon, right? Rather, but you understand it here, so it's okay, fine. The and here we have lambda dash is that of the scattered photon. Now you see the graphite is, we have the graphite as the target atom. So you see that, for example, if we have a photon right here, that photon it passed through the slit, and we have the target, and you see that, look, for example, how it would look like. For example, see here, if we have the nucleus like here, as you see, this is the nucleus, and you know, around the nucleus, this is the electrons are moving in a orbits like this. So this tell us that there is a greater chance that if the electrons are moving, for example, see here, I'll just choose the electron in this valence shell electron like this. So there is a greater chance that at one point the incident photon may strike the this electron, and it may transfer some of its energy to this electron. As a result, which the electron will recoil back and the photon will scatter, right? So like unlike the photoelectric effect, not all of the energy of the photon is absorbed by this electron. A part of the energy is absorbed, and the part of the energy is absorbed here. So now let us see here, look at this. Now I just want to put some mathematics here. So here you see, look, we have the incident photon as you see, and here we have the electron. Let this electron be at rest for a while. So the initial momentum of the electron considered here is 0. The momentum of the electron here, this is 0. The rest mass energy of the electron is m naught into c square, as you see here. And the initial energy of the photon, the energy of the photon is denoted by EF, and it is HF, where H is the Planck constant, 6.63 into 10 to the power minus 34 joule into second. F is the frequency of the incident photon, depends on the wavelength of the X-ray photon. This incident photon is, remember, this is X-ray photon, okay? Ordinary light cannot exhibits this phenomena. Here we have the target electron. Now we, for our simplicity, we only consider that all happens along the X direction only, along the X direction here. That is, the motion of the photon is along the X direction here. So once that when it strikes the electron scatters through an angle pi, while the photon with angle theta, known as the scattering angle. This is called the scattering angle. Now, after losing its energy, after collision, the scattered photon energy changed to this EF, and this the after the energy, and it will be HC by H into F, and then it will become equal to HC by lambda, where this is the photon, this is the initial momentum of the photon. Sorry for that, I should mark the initial momentum of the photon is like this, EF. This is the initial momentum of the photon, and here, and this initial momentum of the photon will be equal to h by lambda, right? And lambda I for if you use the incident symbol, and h by lambda dash if you use it for the scatter is lambda dash. So that is the final momentum of the photon. Now, in order to derive the relation for the to derive this relation, uh, we will use that is, since it is a collision, so we will use two important equation here. One, the law of conservation of energy, the law of conservation of energy, the law of conservation of energy, right? And second, we will use the law of conservation, the law of conservation of momentum. So if we apply these two equations together, then we will come across this equation as you see here. Now let us see. Look, as I told that we consider initially, we say that the photons travel along the x direction only. As you see that the motion of the photon is along the x direction, okay, with all label again here. Now let's see, we have this the x, this is the x-axis, the positive x-axis, and here we have the positive y, the y-axis. Now look, as you see, I told that once the initial momentum of the electron is zero, its rest mass energy is this. After when the electron recoil, then the final energy of the electron become, the initial energy is this, the final energy of the electron will look like this, E, the final energy of the electron. Right, and then after scattering, the photon will scatter with energy this and with momentum this. Now, since as we know that energy is scalar quantity, so we do not have a problem to deal with the law of conservation of energy, but definitely we have a problem by applying the law of conservation of momentum, because we must encounter we must take into account the direction of the momentum also. So here, as you see, look at this, right in the beginning, the total momentum, look, the first, the see here, look, we have the total momentum before collision is this p, the moment, sorry, the momentum of the, as I told, the momentum of the photon, and we denote the momentum of the photon, the initial momentum Pf. This is any subscript, you can write Pp also, but that will maybe create a confusion because we start photon from P. So this is why I use this thing. You can use any symbol, no problem. So see here, it will be equal h by lambda, and lambda I or lambda scatter, or just you may simply write lambda. Now you see here, look, that right at this point, if you see, look at this diagram here, that what happens here, that initially the total momentum of the photon is this one. This is the net momentum of the photon. But right now, if you see that, look, we have one the momentum for what, we have one the momentum for the photon, that is the momentum of the electron, as you see, like this one. So look, if this is the original momentum of the photon, this is Pf, and as you see that the momentum of the electron here is this one. This is the momentum of the electron, right? The electron travel in this direction. So this is the momentum of the electron. For electron, this is the initial momentum of the photon. And you see that we have, look, let me just extend this. And you know, we have another momentum of the this one. As you see, the momentum for what? The momentum for the, this is angle theta. The momentum for the, let's say, the momentum of the photon, like this one. Okay, so now let us first, just this is the, I used here the dot product. Look here, the dot product of the initial momentum and the final momentum of the photon. Sorry, the dot product of the initial and the final momentum of the photon, and I label this equation is equation number 1 here. Now look here, you see the law of conservation of energy. Law of conservation of energy. Now you see that right in the beginning, we have the energy of the photon and we have the rest mass energy of the electron. And it is equal to the energy of the scattered photon. And this is the energy of the scattered electron. Sometimes we call it recoil electron also. Recoil electron energy. Right? So according to the law of conservation of energy, this is the same, and this is the total energy. This is the energy of the photon after scattering. Now you see this is my equation number 2. Now here, this is a very important equation. These 3 equations are the basis for proving the Compton, for deriving the Compton scattering formula. Here, this equation, I label it as equation number 3 here. And these 3 equations are the most important equation. The entire derivation is based here on these 3 equations. Now you see, look, this initial momentum is the sum of this and this. Just look what I apply here, the vector addition. It is what? The vector addition. Because you know that this is what? This is the resultant vector. So the resultant momentum. The resultant momentum. And what is the resultant momentum? Of course, the initial momentum. And this is the sum of the momentum will be taken away by the recoil momentum of the recoil electron. And here this is the momentum of the, right here we have this momentum of the scattered photon. So we have this equation now. Now let us see that what we have done here, that we have actually rearranged the equation here. Now look, I just did it the for this, I made it like this. Okay, this is just, here you see rearrangement here, rearranging equation 2. I hear it rearranged. Now look, so this will be like the EF by C and minus E F. This is the energy of the photon after scattering by C whole square. Now this equation should not confuses you that where does this equation comes from. So easy, as we know that energy, that is energy is equal to what? PC. This is what from Einstein mass energy equation. You know E is equal to what? mc square. So mc into c, so pc. So this is actually the momentum of the photon, and this momentum of the photon is equal E by c. So here instead of the energy, I wrote what, since E is this, so for from that equation I can write E square is what, the p square by c square, the p square by the p square by c square. That is the p square by what, by c square, and then I moved on the c on that side. So here is just a mathematical arrangement here, and here we get the, here we get it like this, p square, and here we have this is the p square. So after the simplification, here is now pure simplification. You can use this, you can do this by yourself. So when you simplify this, then what happens that here you get to this equation, to this, and then after all, you know that this is momentum and this is momentum, and as I already told, that momentum is equal to h by lambda. So for you adjust for the photon initial momentum and final momentum, or the incident photon or the scattered photon, and at the end you will come across with this equation. Now you can see, look, as here, you know that the this is what, this is a mathematical function cos of theta, and it has no unit. So definitely this product has the unit of what, wavelength, and you put the value of Planck constant and not c, and you will get the numerical value. And I'm very sorry that I do not remember it right now by heart, but this is very easy. The Planck constant value, you know, the rest mass of the electron, you know, and the value of c, you know. Okay, so that is how we can derive the Compton effect. So here this equation shows that the momentum of the scattered photon is different, the wavelength of the scattered photon is different than the wavelength of the incident photon, right? So this is how we can explain the Compton effect. So here this tells you that the scattered and the incident photon do not have the same wavelength, where as per classical physics, they suggest it could be the same, but here it is not the same. Okay, so this is how the Compton effect is. Now there are two major differences between Compton effect and the photoelectric effect. This is the effect caused by the inelastic scattering of high energy photon. The word high energy photon here I means intermediate, okay, not that much high in the X-ray range. Because if you consider the high, so that will maybe shift us towards another phenomena known as the pair production, which I will explain in my next lecture. So it is intermediate energy. And the photoelectric effect, this is the effect caused by the weak bound electrons. So as I told, low energy interaction that are ejected from the surface of the material when electromagnetic radiation interacts with the electrons. The wavelength of the scattered photon is higher than that of the incident photon. Here the story is completely different, and this is very important point. The wavelength is not observed as photon disappear after interacting with the electron. So here what actually I want to tell you, that here the photon, what, the photon completely lost, yeah, the photon completely lost its energy. Yeah, the photon energy completely, yeah, I would write not like this, but the photon completely lose its energy to the electron bus. Here it is left with nothing. Here Yes, it is left with. Not all of the energy is lost. Not all of the energy is lost. Only a part of the energy is only a part of the energy is. So this is the all about the Compton effect, which I told is one of the most important features of the modern physics, which describes the particle nature of the radiation. The radiation or light can behave as particle also, right? So this is the end of our lecture today. So inshallah, see you here in the next lecture.